Good evening, everyone. Welcome to Byju's Exam Prep IS. Today we are here with the sixth class on science and technology. But before we start, just a quick check. If audio and video both are working fine, please let me know. Wonderful, all good. So let's begin. So yesterday, unfortunately, as we moved to this new section, all of a sudden, because of some connection issues, the class got shut. So we missed the last half an hour. So we had to start from this particular portion, that is space technology. Now, in space technology, what we basically had discussed is that there are two types. So what I told you, a brief introduction that I had given you yesterday about space technology, is the fact that this is where we'll discuss about the various aspects of how we apply our understanding of space, or everything, that how exactly can we use space. So for example, how we launch satellites and why do we launch satellites, what are the applications of the satellites. So there are all these different things that we are going to study as a part of this portion of our chapter. Now, yeah. So now, first things first, that when we observe the space, how do we observe the space? There are two ways in which we can observe the space. Either it is a ground-based observation or it is space-based observation. Ground-based and space-based. What is the meaning of ground-based observation? Where we are sitting on the ground, relaxing here and watching the night sky, meaning using the telescopes. So when we start using the telescopes for observing the night sky, this is called as ground-based observations. So in this, what we see is that optical and radio telescopes play the most important role when it comes to ground-based observations. Although there are other types of telescopes as well. So for example, our James Webb Space Telescope is an infrared telescope. Similarly, we had our AstroSat, which was a multi-wavelength telescope including X-rays as well. So there are different types of electromagnetic waves which can be used or utilized for making a telescope. But the most important ones are optical and radio telescopes. So the first one is an optical telescope. Now, when it comes to optical telescopes, what we basically know is that optical telescopes will be using the visible part of the electromagnetic spectrum. They use the visible part of the electromagnetic spectrum, meaning that they use the same light that we also use. For example, our eyes, we can see the world because our eyes can perceive this visible light, can perceive this optical light, and that's why we are able to see the world. So something similar is what we observe with regard to the optical telescopes as well. And these optical telescopes, they would be trying to take the picture or take the photograph by capturing the visible part of the electromagnetic spectrum. Now, they obviously become the most important kinds of telescopes for us. Why so? The main reason simply being that the kinds of pictures that you get from an optical telescope will be similar to how we can perceive the world, how we perceive the world. What our eyes see is similar to what an optical telescope sees. So that's why this becomes the most popular of all the different types of telescopes. Now, in this regard, when it comes to an optical telescope, there are various different optical telescopes. The three important Indian telescopes that we have is one at Devsthal in Uttarakhand, second one in Hanle in Ladakh, and then the third one in Javdi Hills in Tamil Nadu. So these are the three important optical telescopes that we have in India. Now, out of these, also the most important telescope that we have probably is the one that we have at Hanle. This telescope that you see right here, this is the picture of the Hanle telescope. Now, when it comes to the Hanle telescope, why exactly it is important is also something to be understood, because it is located in an area which is very, very remote area, very far off from any kind of population, very far away from any kind of settlement. Uh, Hardly you get any tourists who visit these kind of areas. Even the local people, they are very sparse in this area. There is no electricity, there is no mobile phone network. The temperatures are extremely low. Temperatures even during summers will be in the range of -5 to -6 degrees Celsius. During winter, it can go to as low as -20 degrees Celsius, or even beyond that. It is a cold desert area because it is located in the Ladakh region. So it is a cold desert area, and because of that, also what we see is that it remains very isolated. So because of all these conditions, and there are no clouds, no rainfall, hardly 2 or 3 days of rainfall in the entire year is what they receive. So when you look at all these conditions, you understand why this is such an important telescope, why this is such an important place for India, that we placed our telescope here, the optical telescope here. And that's why you might have heard about this, that when it comes to the Hanle telescope, it has been selected as a dark sky reserve. So government of India now has declared Hanle as dark sky reserve. And do you know why dark sky reserve, or what is the significance of dark sky reserve? Why exactly this was chosen? Any idea? What is the significance of dark sky reserve? Sky is clear, very high altitude. That's correct. So the meaning of dark sky reserve is that this is a place for observing. It's a very good place for observing the night sky. A very good place for observing the night sky. So that's why it's very easy. If you go there and if you look at the night sky late at night, when there is no electricity, or uh, there is no light around, you will be able to see astonishing pictures. Being here, let's say, living in a city or in a populated area, you probably do not see more than 10, 20 stars in the night sky. But when you go here, you'll actually be able to observe the entire line of the Milky Way galaxy, which is wonderful sight to have. And that's why, remember why this place has been chosen, because first, very sparsely populated, no light pollution, no light pollution, cloudless skies throughout the year. All right, cloudless skies throughout the year. So that is the reason why this area also has been chosen as the dark sky reserve. And Hanle, one of the research that happened in 2022, in that research, Hanle was seen to be one of the best places in the world to observe the night sky. It's such an important area from this perspective for India. Coming to the radio telescopes will be capturing the invisible radio waves of the electromagnetic spectrum. So they'll be, and now when it comes to radio waves are actually longer waves. We'll discuss this in greater detail when we go to IT and communication chapter. But when it comes to radio waves actually are longer waves, and that's why they can travel longer distances and they can give you observations from longer distances compared to the optical telescope or any other telescope. So that is the significance of radio telescope, that they can travel longer. I mean, radio waves can travel longer, hence the radio telescopes can give you observations from farther distances as compared to any other telescope. So when it comes to India's telescopes, there are two important ones, one in Pune and one in Uti. So this one that you see here, this is located in Pune. So when it comes to radio telescopes, of course, the kinds of pictures that you see, or the images, the observations that are made by radio telescopes, they're very, very different, right? They're very different as compared to the optical telescopes. So, and that's why the kinds of images that we get are very different. So for example, if you look at the difference here, this is a picture that has been taken by an optical telescope, right? Taken by an optical telescope, and this is something that has been taken by a radio telescope. So of course you will be able to recognize the one that has been taken by optical telescope better as compared to the one taken by radio telescope. So now that is where basically we are when it comes to optical and radio telescopes. Now that is about the ground based observations. Coming to the space based observations, and how do we make space based observations? To make any space based observation we need satellites. All right, we need satellites, and satellites become very useful in various different ways. Today we find that there are n number of applications where satellites become very crucial, and we'll discuss all about that in this particular chapter. Now, the very first question is, how do the objects even stay in an orbit? How do we ensure that a satellite that is revolving around the Earth keeps on revolving around the Earth? How do we ensure that? Now, in this regard, something that becomes very crucial is Newton's first law of motion. What does Newton's first law of motion say? An object at rest will remain at rest. An object in uniform motion will remain in uniform motion unless acted upon by an external force. Correct? This is what the Newton's first law of motion says, that the object at rest will remain at rest unless an external force acts upon it. So this is something that is actually used as a theory or as a law for also keeping the satellites in their orbit. Because when it comes to the first law, Newton's first law, it talks about balancing of the forces. It talks about balancing the forces. Let me give you an example. Suppose that you have a box. You have a box which has been kept on a surface like this. All right. Now, on this box, there are forces being exerted. One force from this side, one force from this side, right? So there are forces being exerted on this box. Or from both the sides, we are exerting forces. Now, when we are exerting these forces on this box, if let's say one force is greater than the second, suppose that force 1 is greater than 2, what happens then? It will start moving in the direction of in which force number 1 is being applied. If 1 is greater than 2, and if 2 is greater than 1, then it will start moving in the other direction, in the direction of what 2 is applying. Now in this context, let's say if both are equal, force number 1 and force number 2, if force number 1 is equal to force number 2, what happens then? The box doesn't move, right? The box will not move. Box will remain where it is, and this box will remain where it is, and that is how we will be able to balance the forces and ensure that it is remaining where it is. So when 1 is equal to 2, the box doesn't move, right? The box will not move it if 1 is equal to 2. So something similar is what we will use for placing a satellite into the orbit as well. That if we want that the satellite keeps on revolving at a certain height, right? So suppose that 300 kilometers above the surface of the earth, we want the satellite to always remain at 300 kilometers above the earth. What do we do? How do we ensure that that happens? By ensuring that the forces that are applied on this satellite at 300 kilometers remain the same from all the sides. And if it remains same from all the sides, it will remain where it is. And this is exactly what we do and how we apply these forces. So if you see here, so what we basically see is that on one hand, there are two forces that will be applied for any satellite which is in the orbit. There are two forces. One force which is called as any circular motion. There are two forces that apply. One is called as centripetal force, and the other one is called as centrifugal force. right? Centripetal force and centrifugal force. Now, when it comes to these two forces, centripetal force and centrifugal force, what is centripetal force? Centripetal force is that force that acts in a circular motion towards the center. The force that acts towards the center is called as the centripetal force. And on the other hand, in a circular motion, the force that acts away from the center is called as centrifugal force. Now, if I ask you that suppose that we have the earth, this, let's say this is the earth, right? Suppose that this is the earth, and let's say this is the satellite. So if I ask you, can you tell me which force here acts as the centripetal force? What kind of force is acting as the centripetal force on this satellite? Any idea? Can somebody guess? Tirtha correct, Pathan correct, Niranjana correct, Anil correct, Vivek correct, Paris correct, Viresh correct. Wonderful. Bijo correct, Jamima correct. Everyone is giving correct answers. So this basically is the force of gravitation, right? Because the earth is pulling this satellite towards itself. Correct. The earth is pulling this satellite towards itself, and that's why the centripetal force in this context is the gravitational force. Now we need another force so that we can counter this gravitational force. Otherwise, the satellite will fall on the earth. So what is this force? This force is the force that we are providing. The force due to motion, the thrust that we provide when we are launching a rocket. So that force that we are providing with the help of that fuel, that is called as, that basically acts as the centrifugal force in this context. All right. So this is the centrifugal force here. So centrifugal force basically here is the force due to motion. The force that we are providing due to motion, that is the centrifugal force. And wherever we are able to balance these forces, that is where the satellite will be placed. So for example, if we want the satellite to be placed, let's say at 10,000 kilometers, so we need to ensure that the centripetal force and centrifugal force, both at 10,000 kilometers above the earth, they should be balanced. If they are balanced at 10,000 kilometers, the satellite will keep on revolving at 10,000 kilometers above the surface of the earth. So that is precisely what we have to do. Very simple, just balance the forces. But unfortunately, things are not that simple. Rocket science is called as rocket science for a reason, because there are a lot of variables that I have not talked about, variables that we are not going to talk about anyway, because you are going to appear in civil services examination and not an ISRO based examination. So that's why we don't need to go beyond that. You need to know the basics. The basics are that we are only trying to balance these two forces. Otherwise, there are a lot of variables. For example, everything here is circular and round. Unfortunately, in the real world, everything is not circular and round. So that's why the force being applied at every place is different. Now, Earth also is not a perfect sphere. So that's why the gravity also keeps on varying at every point on the Earth. So that's why you have to account for that. Then there is the atmosphere, and there will be a lot of atmospheric resistance. So we have to account for that. Then when you launch the satellite will keep going up, and it is using the fuel, and its weight is also decreasing. So you have to account for that. Then our orbit is not completely circular in most of the cases. It is elliptical in nature. So you have to account for that. So there are a lot of variables, and it's not only gravity of the earth but other celestial bodies also, which have a little effect on this satellite. So you have to account for that. So there are a lot of these kind of variables that we have to account for to ensure that the satellite remains in its given orbit. So that is when the things start becoming very complex, but we are not bothered about that. For you, the only thing that you need here is understand the basics, and the basics say that centripetal force have to be equal to the centrifugal force, and if these are equal, the satellite will be placed in the required orbit. An interesting question that was asked in your paper in 2011. Please read this question. Can be a bit confusing. I'll discuss this with you, but please try to answer this question on your own first. I'm launching the poll for you. Please mark your answers. So 5% A, 20% B. This I did not expect. 33% C and 42% D. I expected a confusion between C and D. So let me clear this question for you. The artificial satellite orbiting around the Earth does not fall down. This is so because attraction of the Earth. What do we mean by attraction of the Earth? Gravity, right? Does not exist at such height. Is that possible? It's not possible. That's wrong. Gravity does exist. I mean, even the moon, which is as far as 384,000 kilometers away, even that is held by the Earth's gravity. So, how is it possible that the attraction does not exist at such height? That's the force we just discussed. That is the centripetal force. So, A definitely is wrong. B is neutralized by the attraction of the moon. No. What is being, what are we using to neutralize it? We are using the motion. We are not using the moon. First of all, is very small. Its gravitational effect is very small, and the satellite is very near the Earth. So moon is it at no place to have any kind of effect or any substantial effect on this satellite. So that's why it is the centrifugal force that plays a role, which is the thrust that we are providing. Moon does not play any role. So that's why this is wrong. Now coming between C and D. C says provides the necessary speed for its steady motion. D says provides the necessary acceleration for the motion. Now provides the necessary speed for its steady motion. Now first and foremost, the motion is not steady. And what we are applying is force. Correct? We are applying a force. Can you tell me a simple, do you remember what is the formula for force? Force is equal to, yes, mass into acceleration. Correct? Force is equal to mass into acceleration, or it's simply expressed, force is equal to ma. F is equal to ma, where m is mass and a is acceleration. So the force that we are providing, that force is determined by the kind of acceleration that we are providing. Correct? We have to provide acceleration that acts against the Earth's gravitational force. Again, just understand this. When we say speed, why speed is not correct? Because it's not only the speed or the magnitude of the speed, but also the direction in which it is being launched. So both speed and direction matter. So instead of this, if let's say it was velocity, then this would have made more sense. And also, the motion is not steady. The motion is variable. The motion will keep on changing. It's a circular motion. So it keeps changing every second. So let's say if option C was provides the necessary velocity for its motion, then in that case C could have been correct. But when it says speed for steady motion, then it is not correct. What is the difference between speed and velocity? Anyone who remembers? Difference between speed and velocity. Yes, magnitude and direction, correct. So speed has only magnitude, right? Speed has only magnitude, whereas velocity has magnitude and direction both, correct. So that is the difference, and that's why here velocity is what matters. So that's why if c was provides necessary velocity for its motion, if they had omitted the term steady and instead of speed they had used velocity, then c could have been correct. But in the absence of that, c is not correct, and the correct answer will be provides the necessary acceleration for its motion. So it is a difficult question, no doubt. It is a very confusing question, no doubt, but you'll have to think through whenever these kind of questions come. And unfortunately these kind of questions have come and would come. Sometimes they would ask you a question which seems to be too technical in science, but you have to apply everything that you know. You have to think of everything that you have learned from one space or another. Now, coming to the types of orbit. Now, when it comes to the types of orbits, what we understand is that there are various different types of orbits. For example, you might have heard of geosynchronous orbit or geostationary orbit, semi-synchronous orbit, polar orbit, equatorial orbit. So there are different types of orbits like this. But when it comes to all these different types of orbits, just remember that all these different types of orbits, they can actually be clubbed into just three types of orbits: LEO, MEO, or HEO, meaning low Earth orbit, medium Earth orbit, and high Earth orbit. Now let's try to understand what do we mean by these three. What is LEO, what is MEO, what is HEO? Now, LEO, that is low Earth orbit, stands for the orbit which has an altitude starting from 180 kilometers and goes up to 2000 kilometers. 180 to 2000 kilometers. This range is called as the low Earth orbit. All right, this is called as the low Earth orbit. And why low Earth? Because it is near to the Earth. That's why it is called as the low Earth orbit. So 180 kilometers is where more or less you can say our atmosphere ends, the ionosphere ends. So that is why 180 kilometers. And beyond that, up to 2000 kilometers is what we consider as low Earth orbit. Mostly, although the satellites will be placed at 500 to 700 kilometers above the Earth, but up to 2000 kilometers, we'll say that it is low Earth orbit. Then there is the medium Earth orbit, starting from 2000 kilometers and going up to 35,786 kilometers. So between this range of distance from the surface of the Earth, this is called as the medium Earth orbit or mid Earth orbit. And then after that we have the high Earth orbit. And when it comes to the high Earth orbit, it is something that is at or above 35,786 kilometers. Now, one thing, why exactly this figure? Because low Earth orbit, we are saying 180 to 2000. The mid Earth orbit also starts at 2000. But here we see a very specific number: 35786, 35,786 kilometers. Understand the significance of this particular number. This number is where the time period of revolution is of 1 day, of 24 hours. So satellites at this height, satellites at this height complete one revolution in 24 hours, that is 1 day. That is the significance of this number. That is the reason why are we placing certain satellites at this particular height, because this is the height where we see that the satellites will be able to complete one revolution around the earth, one revolution around the earth in 1 day or in 24 hours. One revolution, I'll write this, around the earth. One revolution around the earth in 24 hours. So that is the reason why this exact number, that is 35,786 kilometers. And as you can see, the lunar orbit or moon's orbit is at 3,84,000 kilometers away. So that's why it is very far away as compared to where we are or where we place all these satellites. So that's why the gravity of moon will have no significant impact on the satellites or the working of the satellites. Now then, so first, before we go on to understand the different types of orbits, there are three important factors that determine any orbit. And that's why these factors also are very, very important for us to understand. That how do we ensure that the satellite is where it belongs? So, what are the factors that will determine an orbit? The first factor is height. Now, height is a very, very important factor. Height is a very important factor. So, for example, let me tell you why it is important. Suppose that this is the Earth. All right. Let's say this is the Earth, and there are 2 points. One is A, which is here, and let's say one is B, which is here. So these are the 2 points. One, you can say more or less, this is the low Earth orbit, correct? And let's say this is the high Earth orbit. So height from the Earth is different in these two cases. Now, if I ask you, which is a better point for taking pictures of the Earth? Which is a better point for taking pictures of the Earth? Is it A or is it B? I'm launching a poll for you very quickly. I'll not give you more than 10 seconds here. Do you think A is a better point to take pictures, or is it B, which is a better point to take pictures? Pictures and videos, whatever it is. Hmm. So 39% of you feel that it is A, and 61% of you feel that it is B. Can you tell me your reasons in the comment? Why do you think A or B? What led you to believe that it should be A or B? Hmm. Yeah. So expected what I expected the answers to be. The correct answer, of course, is A. Now, why the answer is A is because when you are at A, you take clearer pictures and videos. You take high resolution pictures and videos. B, as many of you have written, that if you are at B, you will be able to cover a larger area. But just think of this, that suppose that you have your phone camera and you want to click pictures. So when you want to click pictures, do you want to be as near as possible, or do you want to be as far as possible just to cover a larger area? You generally want that you should be able to take a high resolution picture, correct? You want that you should get clarity in this picture, right? So that is the primary objective. Sometimes you might feel the need that I should be able to cover the entire landscape, but in most of the cases you will be taking pictures in a manner that you can get as much clarity as possible, and that you can get when you are near the object, when you are near the subject of which you are taking the picture. This is precisely what applies in case of satellites also, that if you are at A, you are near the Earth, and hence you can take clearer pictures and videos of the Earth. How is that helpful? Take for example disaster management. Suppose that there is a region in India, an area in India which is suffering from floods, right? It's suffering from floods. And if it is suffering from floods, to understand what kind of disaster management mitigation efforts we have to take, for that we first need to have good pictures. We need to have very clear pictures and videos of that particular place, which we can do from A and not from B, correct? B will not give us as much clarity as A would give. So that's why A would give us that kind of clarity which is needed for taking clearer pictures and videos, and hence we'll be able to make better strategy for that particular area. Similarly, we see that there are other military applications, agricultural applications, mineral related applications, cartography applications. So there are many different applications where being near or taking clear pictures and videos will be crucial. So that's why these kind of satellites largely will be placed at A, that is low Earth orbit. So that's why taking clear pictures and videos of the Earth, A. Why? For clarity. All right. So, and then I have another question for you. Which is a better place for placing communication satellites? Which is a better place for communication satellites? Is it A or is it B? Again, launching the poll, I'll give you 10 seconds to answer your question. Which should be a better place for placing communication satellites? So 63% of you believe it should be B, and this is correct. It should be B. Can you give me your reason? Why do you think B is better suited for communication satellites? Yes, Shahid, your answer is correct. Yashika correct. Vishant correct. Prithvi correct. Shimna correct. Wonderful. So this basically is for coverage, or what we call as better range. Because now, is it that we can't place a communication satellite at A? We can. We absolutely can. It's not that you cannot place a satellite at A for communication purposes. You can do that. But the problem will be that you will have to place more number of satellites. So for example, let's say if you see this, suppose that A has this much range. Okay, let me have a bigger Earth for clarity. Let's say this is our Earth. Hmm. So let's say if we look at the range, suppose that A has this kind of range, and parallel to this, if we look at B, B perhaps has this much of range, right? So what then happens is that instead of having one satellite, if you want to cover this much of area, you will have to have multiple satellites at A. So something that one satellite can do from B, you will have to place multiple satellites at A to do the same job. So that's not ideal, that's not cost effective. So that's why we would prefer to place this satellite at B instead of placing the satellite at A. So that's why just remember that it's not that you can't place the satellite at A for communication purposes. You can, but that will have a cost problem. So that is where we see that having a better coverage becomes crucial for a communication satellite. So that's why first factor is height. The second factor is eccentricity. Now, eccentricity is a factor which is related to the shape. Eccentricity determines the shape of the orbit. Now, eccentricity is something that is denoted by E, and the value of E is always between 0 and 1. It can be equal to 0, but it will never be equal to 1. It will always be less than 1. So in this context, when the value of E is 0, it is circular. The shape becomes circular. And when it is near 1, when let's say E is equal to 0.9999, so on. It can never be 1. Just remember this. So when it is this much, then it is a highly elongated orbit. All right. It is a highly elongated orbit when the value is near 1. It cannot be 1. When it is 1, it becomes a parabola, and when it is more than 1, it becomes a hyperbola. So that is not the shape of any given orbit usually, right? So that's why eccentricity will help you determine what the shape of the orbit is. So as you can see, when e is equal to 0, it is a circle, right? At e is equal to 0, it is a circle. And as you can see, when e is equal to 0.9, it is a highly elongated orbit. So that's why eccentricity becomes important for shape. And why is shape important? Sometimes you'll see that there are specific applications where the shape of the orbit also becomes crucial. And we'll take some examples. I'll not show you right now, but there are certain examples that we'll take later, and that will automatically explain you why the shape also matters in a given orbit. So this is the second factor. Then the third factor. The third factor is inclination. Now, inclination is a factor that will determine whether it is an equatorial or polar orbit. So, whether it is a polar or equatorial orbit. So, whether it is a polar orbit or whether it is an equatorial orbit will be determined by the inclination from the equator. So, when you have, let's say, 0 degree inclination, or maybe 1 to 5, 10 degrees inclination, then you will say that it is an equatorial orbit. And when you have inclination like 60, 70, 80 degrees Celsius, then you would say that it is a polar orbit. So again, we'll see that there is a significance of equatorial and polar orbits as well. As we go into this chapter, you will see that it also has an important implication. So that's why these are the three factors. These are the three factors that determine any kind of orbit. They help us in understanding of any kind of orbit. So that is basically what these three factors signify. Now, on the basis of all these factors, we have the different types of orbits. Now, the first kind of orbit that we have here is low Earth orbit. But again, before going there, if you have any questions, last 45 minutes or so, whatever we have discussed, if you have any question, please let me know before we move on to our next topic. Please repeat the three factors. Okay, let me just do a quick recap again. So first factor is height. Height determines application. Height is determined on the basis of application. So if the application is taking pictures and videos, we'll try to be near the earth. If the application is communication, we'll try to go far off from the earth. So height becomes one factor. Second factor is eccentricity. Eccentricity determines the shape of the orbit. So shape of the orbit is also very crucial, because that will help us understand. I mean, that will also be managed on the basis of what kind of application we have, and we'll discuss that later. And the third one is inclination. Inclination meaning that whether it is completely aligned with the equator or is it tilted. So if it is completely tilted, or let's say it has 60, 70, 80 degrees inclination, then in that case it will be called as polar orbit, because then it is aligned with the poles of the earth. So that is how we have these three factors. Meaning of acceleration basically is, you can say, when we measure the change in velocity per unit time. All right, the change in velocity per unit time is called as acceleration. So for example, our cars and scooters, bikes, etc., they have an accelerator. So what does the accelerator do? When somebody takes an accelerator, then in that case what happens is that the speed increases. So speed, if it was 20 kilometers per hour, it increases to 40, 50, 60 kilometers per hour, and so on. So that happens because of accelerator. So what does an accelerator do? it accelerates this vehicle. So that is what acceleration is. This is basically the change in velocity per unit time. Acceleration is change in velocity per unit time. Leaderboard is not shown from the last three classes. Oh, remind me towards the end of the class. I'll show you the leaderboard. It would have skipped my mind. How we use inclination, we'll discuss that as we go into the different types of orbits. You will automatically understand it. Difference between centrifugal and centripetal forces. Centrifugal force is the one that is applied away from the center, and centripetal force is the one that is applied towards the center in any circular motion. If E is equal to more, if E is more than 1, what happens? Then in that case, it is not an ellipse anymore, it becomes a hyperbola. E is greater than 1 for a hyperbola. Radio telescope page. Radio telescope. Yeah, here it is. If E is greater than 0, then planet will come out from gravitational pull of the sun. Is it right? No, I wouldn't say that, because see, even our earth, for example, it does not have a circular orbit. E is equal to 0 when you have a circular orbit. For even our earth's orbit, we have an elliptical orbit. That's why there are seasons, otherwise there wouldn't be seasons. So we have seasons because of the elliptical orbit. So E is already greater than 0 for even the earth, but it is always going to be less than 1. Both optical and radio telescopes in Tamil Nadu. Why? Uh, it's not that we have any particular reason, just that wherever we find good areas, we place the satellites there. Or it's also many a times about the government, the state governments who have, uh, let's say, made it easy for getting that land so that these kind of areas could be taken for scientific research and observation. So that's why it's also about the state government. Many a times many of the state governments haven't been haven't made that very easy for the central governments over the last 70 75 odd years. So that is why. Are these radio telescopes not harmful in any aspect? No, they are not. Hmm. Yeah. So now we have the different types of orbits. So when it comes to the different types of orbits, the first one is the low Earth orbit. Now there are two types of low Earth orbits, as you can see. One is called as the polar orbit, and then we have the sun synchronous orbit. Now polar orbit and sun synchronous orbit, they are not very different from one another. In a manner, we also say that sun synchronous orbit is a special kind of polar orbit. It's a special kind of polar orbit, sun synchronous orbit. So that's why we see that sun synchronous orbits actually are they are that's why they are called as they are a special kind of polar orbit. Now, in this particular scenario, when it comes to the low Earth orbit, there are certain features of the low Earth orbit that you should know. Some of it what we have discussed, and some of it that you should know. So first, for example, the height. So height we know is between 180 to up to 2000 kilometers. Correct? Then the applications. So applications wise, most importantly, they are used for Earth observation. used for Earth observation, for observing the Earth, what we also call as remote sensing. Just wait a minute. Let me use more space for this, otherwise it is very cramped. Hmm. So first, the height. Height is between 180 to up to 2000 kilometers. Second is the application. So application is either called, it basically is Earth observation. Earth observation is what we also call as remote sensing. This is also called as remote sensing. Then, when it comes to this orbit, one thing that is very, very important is that when it comes to the orbit period is of just 1.5 to 2 hours, meaning that it takes 1.5 to 2 hours for the satellites placed in this orbit to complete one revolution. To complete one revolution around the Earth, they would take 1.5 to 2 hours. So, again, this is also very, very important. And then the launcher that we use, the launcher that we use largely are PSLVs. I will discuss about PSLVs later. PSLV stands for Polar Satellite Launch Vehicle. So, because it is largely launching the satellite into the polar orbits, that's why it is called as Polar Satellite Launch Vehicle. So, we'll discuss about that at a later stage. Then, the life cycle of the satellites that are placed here in this orbit mostly are 3 to 5 years. Right, so they would remain in the orbit for 3 to 5 years before becoming defunct. So that also is one of the important points. And then when it comes to the low earth orbit, one more important point from this perspective is that largely they are polar orbits. Right, largely these are polar orbits or sun synchronous orbits. So sun synchronous orbits or polar orbits is what we have in the low earth orbit. So that's why you can say that these are some of the important points with regard to whatever what we have. And let me just add one more point here, that they carry lightweight satellites. Largely what we see is that here we place lightweight satellites. All right, lightweight satellites. So meaning that these are largely less than 1500 kg. These are largely less than 1500 kg. So these are lightweight satellites. So that's why in this case we see that these are the different types of, you can say these are some of the properties of the low earth orbit remain with regards to it. Now when it comes to low earth orbit, we are saying that there are two types of orbits. One is polar, one is sun synchronous orbit, where sun synchronous orbit is a special kind of polar orbit. Now why am I saying that it's a special kind of polar orbit? What is special here? So now just look at the name. The name says sun synchronous orbit. So what do I mean by sun synchronous orbit? So the meaning of sun synchronous is that this is a satellite, or this is an orbit where the movement of satellite is synchronized with the sun, synchronized with the local solar time of a place. So here what we do is that the movement of the satellite at sun synchronous polar orbit is synchronized with the local solar time of a place. What is the meaning of this? What do we mean by local solar time of a place? Now, you know this. For example, let's say when it comes to India, we use an Indian standard time so that there is no confusion and there is no regionality in the time that we are following, correct? So that's why Indian standard time is what we follow. But are the movements of the sun all across the country similar? No, right? So, for example, let's say when the sun rises in Arunachal Pradesh, it will still be night in Gujarat. And by the time the sun reaches Gujarat and it is sunrise in Gujarat, Arunachal Pradesh already would have seen at least 1.5 hours of sunlight. So the local solar time is different. So when we sync the movement of the satellite with the local solar time, this is what we call as sun synchronous orbit. So what happens is that for what we basically do is that if let's say a satellite which is at sun synchronous orbit, if it let's say passes over Delhi at 10 a.m. in the morning, then every day at 10 a.m. it will be overhead Delhi. Every day 10 a.m. overhead Delhi. So this is how we synchronize with the local solar time of a place. That's why we are saying that it is synchronized with the local solar time of a place, because if it is let's say overhead at 10 a.m. or 12 a.m. or whenever it is, then it will exactly be overhead the next day at the same time. So that's why it is a sun synchronous orbit, and it becomes a crucial, or let's say a special case of polar orbit. So this means that it passes overhead a place exactly at the same time every day. So this is what we mean by sun synchronous orbit, or having synchronized with the local solar time of a place. So applications wise, there are all these different applications for which we can make the use of a any satellite placed in the low Earth orbit. So these are all the applications, and all these applications, the list actually I've taken from ISRO website. ISRO has listed that these are the different ways in which we are making the use of the Earth observation satellites which are placed in the in the low Earth orbit. So that's why they're all used for Earth observation. So these are all applications of Earth observation or remote sensing satellites. All right. So this is basically what we see, and all these are various ways in which we can use it. And primarily objectives are the same: taking pictures and videos. So wherever we need to take pictures and videos or observe the Earth, that's why it is called as Earth observation satellites. And there are various examples. So for example, we have Cartosat series satellites, OceanSat series satellites, ResourceSat series satellites. So all these are different types of Earth observation satellites. So these mineral sat, resource sat, resat, there are different types of satellites. So that is how we see that Earth observation satellites have been used by India. Then we come to medium Earth orbit. Now, in case of medium Earth orbit, there are two types of orbits. One called as the semi-synchronous orbit, and the second one called as the Molniya orbit. Now, when it comes to the semi-synchronous orbit, this the height of this orbit is placed at 20,200 kilometers above the surface of the Earth. 20,200 kilometers. Then orbit period here, orbit period is of 12 hours, meaning that it completes one revolution around the earth in 12 hours, and that is why we are calling it as semi synchronous. All right, that's why the name semi synchronous has been given, because it completes one revolution in 12 hours, meaning two revolutions in a day. And that is the reason why it has been placed at 20,200 kilometers, because at this height, for completing one revolution around the earth, it would take 12 hours. Now this particular orbit is used by GPS. This particular orbit is used by GPS, and that is the value of semi-synchronous orbit, that it is something which is used by GPS at a height of 20,200 kilometers and an orbit period of 12 hours. So that is where we have our semi-synchronous orbit. The second orbit is Molniya orbit. Now, Molniya orbit is very interesting. This is an orbit that was designed by Russia, or we rather say that it was invented. It was invented by Russia. All right, it was invented by Russia. And why exactly did they invent it? They invented it because this would something that would help in placing their communication satellites. Now the question is why? Because generally speaking, what we discussed is that the communication satellites are placed in the high Earth orbit, right? They are placed in the high Earth orbit. But why is Russia placing its communication satellite in the medium Earth orbit? Understand this. If you look at this picture that we have right here, this picture is of semi-synchronous. Sorry, this is the picture of the Molniya orbit. This is exactly the Molniya orbit. Now understand what is special about this Molniya orbit. Do you see how much inclined it is and how elongated it is? It is very highly elongated. Now, when it is very highly elongated, that's why the second factor that we had spoken of, that when it comes to the shape or eccentricity, it also matters. Here, eccentricity matters, and understand in what way it matters. Generally speaking, we keep the satellites, the communication satellites, in the equatorial orbit, right? They will be placed in the equatorial orbit like this. So for example, let's say we have a satellite which has been placed here. Now this satellite would have a coverage like this. Suppose that this is the coverage of this satellite. Now what happens is that with this coverage, it is not able to cater to the north and the south poles properly, right? It's not able to cater to north and the south poles properly. And Russia has a large landmass, a large part in North Pole, at the North Pole, in the Arctic areas. So then in that case, a communication satellite that is placed in this kind of an orbit, like an equatorial orbit, it is not very helpful for Russia. For the Russian communication needs, it is not very helpful. And that is where Russia thought that we will have to build another orbit so that we can cater to the requirements of Russia in case of communication. And this is when they designed or invented the Molniya orbit. And this is the Molniya orbit, as you can see, that it is a very highly elongated orbit. Now, being highly elongated, what happens is that the satellite will be spending a lot of time in the northern hemisphere, right? It will be spending a lot of time in the northern hemisphere, and very quickly it will come out of the southern hemisphere, because it has not been considered or not been constructed or designed for southern hemisphere. So in this manner, Russia was able to solve its problem by inventing this orbit. Now this is the Russian side of the story. There is another side of the story, and that's the side of the story that comes from the US. What the USA said when this Molniya orbit was designed or invented, US said that they are lying. These Russians, they are lying, and this is not meant for communication needs, this is an orbit that Russia definitely will use to place their spy satellites. This is where the spy satellites will be placed, because this is an orbit which is new, where we do not have any presence. None of the other countries have any presence. So this is an orbit that they can very easily misuse, and they are for sure going to misuse it, and they are going to use it for placing their spy satellites. And the Russians are lying, and they are not going to place their communication satellites there. Now, this was the time of the Cold War, and whatever Russia would do, or USSR rather, at that point of time would do, US would never believe it. Whatever US would say, USSR would never believe it. So that's why these kind of things kept on happening. But we probably would want to believe the official story rather than the conjectures from the other side. So this is basically medium Earth orbit. Now, medium Earth orbit, largely what we see is that medium Earth orbit will be used for navigation. All right, medium Earth orbit largely will be used for navigation, although India doesn't entirely use the medium Earth orbit for navigation. Although some of the other systems of the world, they are placed in the medium Earth orbit, but Indian navigation system is a mix of medium and high Earth orbit. All right, so for example, we have Gagan. We have the Gagan system, and this Gagan system is based on two satellite sets, the GPS and the GSAT satellites, where you have GPS, which is of course in the medium Earth orbit, and then we have the GSAT satellites, which are placed in the high Earth orbit. So that's why what we see in this particular scenario is that in the Gagan system that we are making the use of two sets of orbits, medium Earth orbit and high Earth orbit. And as far as Navik is concerned, it is completely based on the GSAT satellites, or rather the Navik satellites. So we have the IRNSS satellites, which are all placed in the high Earth orbit. So that's why the Indian navigation system is a bit different. It's a combination of medium Earth orbit and high Earth orbit. But largely, when we talk about navigation, you'll find that many of the other countries, they have their navigation satellites placed in the medium Earth orbit. So now, in this particular scenario, when it comes to these satellite systems, the first satellite system that India uses is the Gagan system. And this Gagan system that we see right here, this is, as I told you, that it is a mix of geostationary satellites and the GPS satellites, and they provide all the navigation and positioning services that are required for Gagan to function. Now, why is it called as Gagan? Because it is GPS aided geo augmented navigation. So GPS aided geo augmented navigation. That's why GAGAN, Gagan. So you get the GAGAN from here. Now, this is basically a project that was implemented by the Indian Space Research Organization, or ISRO, along with Airports Authority of India. So they have come together, and they basically have implemented this project or this system called as Gagan. And why? Largely for civil aviation. The main objective is civil aviation, to help civil aviation in various ways. How exactly does it help? First, it helps in reducing the path length. Reducing the path length of flights. That is the primary objective. Now, what it does is that, of course, it will reduce the time of flight as well. So it reduces the total time of flight. So that also is there. And then, of course, because of that, it also saves fuel. So it reduces cost, reduces fuel consumption. and thus also reduces the cost involved. Right? So it reduces the cost involved. So that's why we see that there are all these things, all these important areas when it comes to civil aviation. That how does it help civil aviation? So provides better navigation, reduces the path length of the flights, reduces the time of flight, reduces the fuel consumption, and hence it also reduces the total cost which is involved in the functioning of the Gagan satellites. Now, in this particular scenario, that's why when we look at the Gagan system, it is operated through the GSAT series of satellites. So, GSAT series of satellites plus helped by the GPS system. Now, it's not that it is only going to help in civil aviation. Gagan system is also going to be helpful for a lot of different applications. What kind of applications? It helps in transport, highways, railways, surveying, all these different types of uses is where we see that this Gagan system becomes helpful. So this is the first navigation, this is the first kind of navigation system that India is using for various purposes. And then we have IRNSS, that is Indian Regional Navigation Satellite System, also called as NAVIC. Right? Also called as NAVIC. NAVIC standing for Navigation through Indian Constellation of Satellites. So that's why NAVIC is another name that has been given to IRNSS system. Now, this IRNSS is a system which consists of a total of 7 satellites, 3 geostationary satellites, and 4 geosynchronous satellites. So, we'll discuss about that also. What is geostationary and what is geosynchronous? A little later, we'll have a discussion on that also. So, overall, this is something that becomes, you can say, the Indian GPS. You might have used Google Maps or any kind of maps for going from one place to another, for example. So these maps, these Google Maps or any kind of maps, they are based on these kind of navigation satellites. They are based, they get their information from these navigation satellites. So these navigation satellites largely they are based on GPS. All across the world, largely they are based on GPS. But in India, we want to replace GPS with IRNSS, and that is why IRNSS system has been set up. So this that's why it covers, that's why it is Indian Regional Navigation Satellite System, because it covers India and up to 1500 kilometers beyond the Indian borders. So as you can see, a set of 7 satellites. You have geostationary satellites. So this is a geostationary satellite. This is another geostationary satellite, and this is another geostationary satellite. And here we have geosynchronous satellites also. So we have GSO1, GSO2, GSO3, and GSO4. So that's why we see that there are all these. We'll discuss about geostationary and geosynchronous satellites a little less later. So just hold on for now. So that's why Indian satellite system to provide positioning, navigation, and timing services to users all over India as well as region extending up to 15 kilometers from its 1500 kilometers from its boundaries. Now, one more important aspect of this IRNSS system is that there are two types of services that we get from here. One called as the standard positioning service, and the other one is called as restricted service. The same restricted service is also called as precision positioning service or system. So it is also called as precision positioning service or restricted service. So this is an encrypted service that provides only, which will be provided only to the authorized users, only to the users who are authorized to go into a certain area or have access to a certain area. Only they will have the access to the restricted service. For everyone else, the standard positioning service will be available. And this is something which is very, very important for Indian security. because with GPS you cannot guarantee that. With GPS, what will be open, what will be restricted, all these things are very difficult to determine. But with Indian system, it becomes easier to do that. That we can hide the sensitive areas of the country. For example, wherever we have our missiles or our satellites, etc. So these kind of areas can remain hidden from the maps, which is again very, very crucial. So that's why this IRNSS system becomes very crucial from this perspective. And here, when it comes to IRNSS, we see that it can have an accuracy better than 20 meters, or it can have a much better accuracy actually for the Indian subcontinent, at least compared to the GPS, right? So compared to GPS, it will provide better positioning services in India because it has been designed keeping Indian requirements in mind. So that's why it's going to provide services which are better in India as compared to whatever GPS has been able to provide until now. So that's why this IRNSS system becomes very, very crucial. And that's why today we see that uh, we have started using the IRNSS systems, and we are replacing the GPS systems wherever possible. A lot of mobile phone networks, they are now providing IRNSS networks instead of GPS. The first company in India, for example, the first mobile phone company in India was Xiaomi, uh, which introduced IRNSS in its mobile phones. Of course, it's a Chinese company, so it has to do all that it can do so that it can be here in India without having any threats of any kind of bans. So now in this particular scenario, that's why we have to understand that it becomes a very important system. And the government of India, then we saw that all the other companies also which are there in India, they also started providing IRNSS networks in their mobile sets. Only two companies had not done it initially, the two of the biggest manufacturers in mobile phone world, Samsung and Apple. So Apple and Samsung, they also have been advised by the government of India that they should also start moving to IRNSS as quickly as possible. So this is where we are with IRNSS right now. Then after this, we also have the Global Positioning System, or GPS. Now, as I told you that GPS is in the medium Earth orbit. It is a constellation of 32 satellites currently. And why 32 satellites? Because it is global. In Indian system, we have just 7 satellites. Why? Because it is only supposed to take care of the Indian area, right? So only the Indian borders, the Indian subcontinent and Indian waters. So but global positioning system, GPS, is having a presence globally. So that's why it's a set of 32 satellites in total, and not just 6 7 satellites. Now in the context of GPS, what we see is that they use something called as triangulation. And not only GPS, any navigation system is based on the concept of triangulation, or trilateration also, as it is called sometimes. So what we do here is that instead of using just one satellite to provide positioning or location services to one area, we use a set of three different satellites so that we can improve the accuracy. We can improve upon the precision by using three satellites for one given area. So that's why, if let's say coverage wise, if these kind of areas are being covered by any satellite system, then the satellite system will be able, all these satellites together will be able to provide a better location and services instead of just using when we were using one satellite. So that's why triangulation. So this is what triangulation is: using set of three satellites for improving the accuracy of navigation. For improving the accuracy of navigation, we use a set of three satellites, and this is called as triangulation. So that is why we see that this becomes crucial in the context of GPS. Read this question. This was asked in your 2018 examination, a very, very simple question. I'm launching the poll for you. It's a very simple question. Please answer this. Hmm. So interestingly, only 48% of you have given the correct answer. Question says, with reference to Indian Regional Navigation Satellite System, consider the following statements. First is, IRNSS has 3 satellites in geostationary orbit. This is fine. And 4 satellites in geosynchronous. This is also correct. So first statement is correct. IRNSS covers entire India and about 5,500 square kilometers beyond its borders. This is wrong. We discussed that it covers up to 1,500 kilometers beyond Indian borders. So that's why this is wrong. India will have its own satellite navigation system with full global coverage by the middle of 2019. See, middle of 2019 is already gone 5 years back, and we still don't have a global coverage. So you should know that this is wrong, right? This is wrong, and there should be no doubt about this. And also, it talks about full global coverage. We are not bothered about full global coverage. It's an Indian regional navigation satellite system, because we are concerned only about the Indian region, and it's not about other parts of the world. All right, so that's why 3 is also wrong. So correct answer, that's why, will be A, that is only one. So let's hold on here. Let's take a break here before we go on to high Earth orbit discussion. Meanwhile, if you have any questions from whatever we have discussed in the last half an hour or so, you can post all your questions. Let us take a break here, and on the other side of the break, we'll continue with our discussion and continue with this chapter. So right now the time is 6:27. Yeah, so let's be back by 6:40. Let's be back by 6:40 p.m. and continue with our discussion. Meanwhile, please post all the questions that you have. When I come back from the break, I'll first answer your questions and then we'll move on. Welcome back, everyone. Let's begin with your questions first, and then we shall move to the next topic. Once again, repeat the name of the China mobile company. It's Xiaomi, the Mi or Redmi phones, what you get from there. That I'm talking about. So they were the first ones who implemented IRNSS in India, in their, I mean, their mobile phones. Geofiber or any internet source is harmful for our cells of the body? Not really, not directly. There are some, you can say, corner uh, uh, these researches that have happened, which have given some reports. But I would say that 99 out of 100 researchers have shown that there is no problem as such. There are only one or two here and there who have expressed concerns over the radio waves that are emitted from these sources. But mostly, most of the researchers they have uh, suggested against something like that. Why India replaced GPS? So see, why India wants to replace GPS is very simple reason that GPS is foreign. Now, because of that, it means that all the location, all the positioning, every data that we have, all this data is going to a foreign company, right? Or rather, not a company, but rather GPS is handled by whom? GPS is handled by the Air Force, the US Air Force. So, in a manner, we are handing all the location data to US Air Force. So, that's not good for our security, correct? It's not good for our security. So, that's why we don't want it in their hands. And a realization that happened, you can say, in a manner, was back in 1998 and 1999. In 1998, when we did the nuclear test at Pokhran, this is where we realized, uh, and at the time of Pokhran test, the US satellites, the US GPS satellites, they were trying to keep an eye over India because they had some hunch, they had some information that India might do a certain test. So we had to keep it very secret so that we could hide from the eyes of these satellites. So 1998 this happened. Then 1999 we needed their help during Kargil war. We needed their help because we know what had happened, that Pakistan already was infiltrating in the uh, you can say from the Pakistan occupied Kashmir side to the Indian ministered Kashmir side. So they were coming from the occupied territories towards the they crossed the line of control. So now in this case, we asked US for help, that we needed the location services there to understand the positions of Pakistan because Pakistan was at fault here. And at this point of time, US declined. US did not provide us with the information that we needed in this particular area in Kargil. So these two incidences, in a manner, you can say that these were eye openers for India. That why we need to have our own satellite system, our own navigation system. And this is when we see that in 2001, after that, during the time of the Atal Bihari Vajpayee government, this project was sanctioned, and we started building our own IRNSS network 2003 onwards, and 2013 finally we completed this entire project, and then we started launching the IRNSS satellites, and today we have a constellation of satellites which is IRNSS. When the life cycle of a satellite is over, then what will happen to the satellite? The satellite will basically become defunct. Either it will remain in the same orbit, many a times it will fall towards the earth, it will disintegrate in the atmosphere itself, it will fall into the Pacific, or it can just go the out of the earth's sphere itself. So all these three possibilities remain. How to update our science and tech notes along with current affairs? See, current affairs is something that you keep on adding daily. in the newspaper, or maybe through the newspaper analysis, through the webinars, through any source that we are providing you, try to use these sources. So for example, even if you look at today's news analysis, I only had did today's news analysis, and there were two important science based articles that I discussed. One was with regard to typhoid, so I discussed something related to typhoid and the problems in diagnosis of typhoid. And then the second was with regard to solar energy, that how India has surpassed Japan with solar energy production. So there are two important updates that I discussed today. So similarly, in the news analysis, we keep on discussing some important articles which are related to one portion of our curriculum or the other. So keep updating your notes with the same, and not don't do it date wise, or don't do it weekly or in that manner, but rather do it topic wise. So for example, we have already discussed the topic of solar energy, so try adding this topic to solar energy notes. So that's why this is how you should do it, so that you have a comprehensive set of information at one particular place. Very important. In Google Maps, why India map is blur and other countries' image clearer? See, it depends on when the image has been taken and what kind of image has been taken, what are the permissions that they have from a particular government. So all these things matter. But it's not the case. Even in India today, you'll see that Google uh, map images are pretty clear and everything is available. What we understand when somebody says polar orbit, it simply means that they're aligned with the Earth's poles. So you will know that Earth has a pole which is tilted by 23.5 degrees. So that pole, so it is aligned with this pole, it is revolving around the Earth aligned with this pole. That's why polar. How Gagan system helps to reduce the path length of the aircrafts. So when it comes to the path lengths of aircrafts, there is something that we call as circling approach, something which is called as circling approach. So circling approach means that the flights will not take a direct path, but rather they would take a curved path. I don't know whether you have tried using maps while you are on a flight. If you do that, what you'll find is, so for example, let's say that there is a flight which is coming from Kolkata to maybe Bangalore. So in this case, it's not that it takes a direct flight like this, direct path like this. It would take a curved path, maybe somewhere around this way is how it would have taken the entire path. So that's why this entire path is called as the circling approach. And the Gagan satellites, all right, the Gagan system will help in reducing this, so that we don't have to take this longer path, and we can reduce this path with higher accuracy. That is how it will be able to reduce this path. Nilanjana, can you just send an email to me so that I'll share it with the team who can help you with your problem? Uh, Sir, explain reason given by Russia behind designing Molniya orbit. The reason, the reason is that the normal communication satellites that we have, they are placed in the equatorial orbit, and the range doesn't cover the poles. The range is not able to cover the north pole and the south pole areas. So that's why, because Russia has a large landmass in the north pole area or near the north pole area, that's why Russia felt this need that they would have to have their own satellite system where they can actually cater to the needs of communication in these areas. Can we not ask any doubt during Hindu analysis? No, the live comment is not on there, and also, I mean, it's very difficult for us also to focus while that goes on. Otherwise, it will be a very long session. But if you have any doubts, if you are a student, you don't have to be worried about it. You can always send an email to us. Either send it to Target IS or any of these emails, Or you know my email also. You send it to me. I'll answer your questions. Is 5G harmful to our health? I wouldn't say that. See, most of the researchers have found that there are no problems. There have been one or two researchers here and there that have shown some concerns, but only one or two researchers is not enough when 99 others are showing that there are no problems. Low Earth orbit explained. So, no, low Earth orbit is nothing but an orbit which is near the Earth. That's why low Earth orbit. So, up to 2000 kilometers from the surface of the Earth is where you have low Earth orbit. Please show the Earth observation slide. Earth observation. Here is Earth observation slide. Does Google Maps use IRNSS in India? It depends on what are you using. I mean, depends on what mobile phone are you using, or what system are you using, or whether that company is already aligned with IRNSS or not. If the company is already aligned with IRNSS, then you are getting Google Maps with IRNSS. If the company is not aligned, then you are getting it with GPS. How IRNSS is different? Different from what? Can you just specify this? Is there an effect of space debris from satellites? We'll discuss this. That's the last topic of our discussion in this chapter. Probably tomorrow we'll have a discussion on it. How to set the path in case of Molny? I mean, it's a pure mathematical calculation based on which the path is determined. Why are they using circling path? The reason for that is that it's not very easy to follow a straight line path. Also, there is the rotation of the earth that also changes the path, and then the aspect of the velocity at which they are traveling, that also makes it very difficult to follow a straight line path. And the location services, the navigation, the accuracy or precision of navigation also is a concern. So there are all these things which in total make it difficult to follow a shorter path, and that's why additionally we want the government system to help in it. My email id I've given before also. This is my email id, rashesh.kumar at byju's.com. Is there any political reason behind development of IRNSS? I wouldn't say that. I would say that largely this is security based reason. Can you just tell us again the orbits? Which orbit, Ramandeep, I'm asking you. How the different orbits are discovered? They're not discovered. We design these orbits. All right, so we determine that, okay, this is where we want to place a satellite. So it's not that it was already there and we discovered it. We are designing it. We are calculating mathematically where do we want to place our satellites, and we are placing the satellites there. All right. How is IRNSS going to help us? Uh, help us will still have their satellites on us. See, now they will officially not be allowed to have the Indian data, and they can't do that. Now we also have anti-satellite missiles, so that nobody dares to do any kind of spying over India. How IRNSS is different from GPS? The very simple thing is GPS is global, IRNSS is local, meaning Indian subcontinent only. The accuracy of IRNSS in the Indian subcontinent will be better than GPS. That's another point. Then IRNSS we know has been placed in the high Earth orbit, whereas GPS has been placed in the medium Earth orbit. So these are some of the notable differences between IRNSS and GPS. So MRO GPS height is 20,200 kilometers only. Can it extend up to 35,000 kilometers? Theoretically, yes, but they don't do that. They have placed the satellite at a given position. How much science and technology important for PCS exam? See, state PCS examinations are a bit different from UPSC in many of these cases, because what we find there is more of general science, more of direct physics, chemistry, and biology than asking questions based on whatever discussions we are doing. Example of low Earth orbit, I told you polar orbit and sun synchronous are low Earth orbits. What happened about annotation still not available? I think it is now available because I was told yesterday that it has now been made available. I'll just check with the team once again after the class. Is it the best way to connect toll gate interconnected with IRNSS? We actually are going to try that very soon. Let's see what happens. The Earth's orbits. So Earth's orbits, we know that there are three orbits: low Earth orbit, medium Earth orbit, and high Earth orbit. Low Earth orbit up to 2,000 kilometers above the surface of the Earth, medium Earth orbit up to 35,786 kilometers, and high Earth orbit at or above 35,786 kilometers. So these are the three orbits, and depending on the application, depending on the use, we use different types of orbits like this. Hmm. So let's take in a lot of questions. Let's move to our next topic. Hmm. So the next topic that we have here is high Earth orbit. Now in high Earth orbit, again, there are two types of orbits as you can see on the screen. One called as geosynchronous orbit and the other one is called as geostationary orbit. So geosynchronous orbit is also denoted as GSO and geostationary Earth orbit is also denoted as GEO. So GSO and GEO. Again, looking at some of the important aspects of high Earth orbit. First, the height. Height is at or above 35,786 kilometers. The applications, largely, they are used for communication purposes. Largely, they are used for communication purposes. Then the satellites, the launcher rather that we use, there we had discussed in low Earth orbit that we generally prefer using PSLVs or polar satellite launch vehicles. Here we use GSLVs or geosynchronous satellite launch vehicles. Then after this, the orbit period, as we had discussed, that it is of 24 hours, completes one revolution in 24 hours. So that's another important point. Then these are equatorial orbits. These are largely equatorial orbits. So low Earth orbit, we discussed that it's largely polar, and here it's largely equatorial in nature. Then after this, when it comes to uh, another important point from the perspective of your examination, the life cycle. The life cycle can be up to 15 to 20 years. So it can last, one satellite can last for 15 to 20 years. And then lastly, one more point, as we had discussed there as well, that usually this is where we launch heavier satellites. This is where we launch heavier satellites, that is more than 1500 kg. And usually that's a, if you look at a communication satellite, Communication satellites largely are very massive. I mean, they are bulky. So, for example, they can be 2,000, 3,000, 5,000, 6,000, even 7, 8,000 kilograms. So, they can be very bulky. And on the other hand, the Earth observation satellites or the remote sensing satellites, they are like 500, 700. So, 500 to 700 kg. Whereas communication satellites can be as uh, heavy as 6,000 to 7,000 kilograms. So that's why we understand that these are some of the important properties, and also understand how to also see all these properties together. So for example, we are using GSLVs for heavy satellites, right? We are using GVS for heavy satellites. We are using GSLV for a satellite that is supposed to be placed in the high Earth orbit, where you also have the requirement of communication. So just understand how to link all these together. I'll give you one example. Very interesting question that was asked in your paper. It was at the time when Astrosat was launched by India. Now, to launch Astrosat, we use PSLVs. And generally, you'll see that in most of the cases, we are using PSLV unless it's a very heavy satellite or it is a communication satellite. So only in these cases you might see that a GSLV is being used, but largely otherwise you'll see that PSLVs will be used as far as possible. All the Earth observation satellites, all the IRNSS satellites, even though they are going beyond the low Earth orbit, uh, Astrosat was launched using PSLV. The very recently launched Aditya L1 mission was launched using PSLV. So you'll see that in most of the cases we use PSLV. We prefer PSLV unless we have a very bulky satellite like Gaganyaan mission where we'll use a GSLV. So now Astrosat was launched using a PSLV. One of the statements in the question that was asked was that Astrosat weighs 2000 kg. Now, is it possible that Astrosat, which has been launched by a PSLV, can be of 2000 kg? The answer is no. It's not possible. Why is it not possible? Because PSLVs are not capable of carrying something that is beyond 1500 kg. So that's why you don't even need to know whether Astrosat was 15, whether it was 2000 kg or not. You just know that it was launched using PSLV, and that's it. That's enough for you to mark the answer. So even though it seems to be a factual question, it's not a factual question if you understand the concepts well. So that's why these kind of things that they become important, that how indirectly many a times they help you in your paper. Now let's try to also understand, in this case of geostationary Earth orbit, we again say that this is a special kind of geosynchronous orbit. It is a special kind of geosynchronous orbit. Why? Why are we saying that? Let's try to understand some of the comparison points between geostationary orbit and geosynchronous orbit. That why am I saying that it's a special case of geosynchronous? Now we discussed that orbits, they basically, there are three major factors that determine an orbit, correct? First was height. Now height for both are the same. Height is the same for both, 35,786 kilometers. Height is the same. Second was eccentricity or shape. Now, shape wise, geosynchronous orbit is elliptical as usual. It is elliptical in shape. But when it comes to geostationary orbit, it is circular. It is circular in shape. The third thing that we had discussed was inclination. Correct? So these were the three factors. Now, inclination wise, when it comes to geosynchronous orbit, here small inclination is possible. small inclination from the equator is possible. But when it comes to geostationary Earth orbit, it has a 0 degree inclination. It has a 0 degree inclination from the equator. So it has a 0 degree inclination from the equator. So this is the third point. Now understand this. Because of these 3 points that we are discussing here, geosynchronous orbit, there can be multiple geosynchronous orbits. Why? Because first it is elliptical. So eccentricity can change. It can be highly elongated, it can be less elongated, and all those things are possible. The value of E can be 0.5, 0.7, 0.9, 0.99, whatever we want. But geostationary orbit is circular and at a fixed height. Correct? Circular at a fixed height. Meaning what? That the radius is fixed. This height is what? This height is like the radius. So the radius is fixed and it is circular. So it is fixed in that sense. And then inclination wise also, there is no inclination. So it is a unique orbit. So that's why this geostationary orbit, it becomes a unique orbit, meaning that there is only one geostationary orbit, right? It is a unique orbit. There is only one geostationary orbit. But in case of geosynchronous orbit, first you can have multiple inclinations, 5 degrees, 3 degrees, 7 degrees, above or below. All that is possible. Plus it is elliptical, so various shapes are possible in elliptical also. So that's why here there are multiple possible orbits. Multiple possible orbits in case of GSO. So that is basically what we see in case of GEO and GSO. And that's why we are saying that geostationary orbit is a special case of geosynchronous orbit. Why? Because all the parameters are fixed here. They're not different, they are fixed. That's why it's not different from geosynchronous orbit. It is a special kind of geosynchronous orbit. That's the better way to say it. Don't say that geostationary orbit is a different orbit and a geosynchronous orbit is a different orbit. No. Geostationary orbit is a special kind of geosynchronous orbit because all the different parameters are fixed in a geostationary orbit, which can be variable in a geosynchronous orbit. That is the basic difference why we are saying that it's a special orbit. So as you can see that geostationary orbit, it lies in the plane of the equator, right? It lies in the plane of the equator. This is the equator, correct? This is the line of the equator. So that's why it lies on the plane of the equator, whereas geosynchronous orbit can be a bit tilted. So that is the basic difference between geostationary orbit and geosynchronous orbit. Now, usually what we see is that for satellite communication, we'll be making the use of high Earth orbit, either geostationary or geosynchronous. So various different ways: telecommunication, telemedicine, teleeducation, television, mobile communication, radio communication. In all these cases, satellites can be used. What satellites? Communication satellites can be used. So that's why these all satellites, they are called as communication satellites. So there are two systems of communication satellites, the INSAT system and the GSAT system. Initially, when we started launching our own communication satellites, this is where we used to have INSAT satellites. All right. This is where we used to have INSAT satellites, and these INSAT satellites were being launched by India, but with not with our own launchers because we did not have the GSLV back then. So we used to take help of largely France, sometimes Russia. So either France or Russia would do our launching. But then we developed our own GSLVs back in 2001, and then we started launching our own satellites, our own communication satellites, and then a new naming was done, that is GSAT. So it's not that INSAT is not used anymore. Still, we keep using INSAT names once in a while, and GSAT also are communication satellites. So all these are the two systems of communication satellites that we have here in India. Read this question. Very simple question. Let me launch the poll for you. It's a very simple question. I hope most of you get it correct. Please mark your responses. Good. 66% of you have marked the correct answer, which is A. Satellites used for telecommunication relay are kept in a geostationary orbit. A satellite is said to be in such an orbit when first, the satellite is geosynchronous. So we discussed that geostationary orbit is a special kind of geosynchronous orbit. So yes, the orbit is geosynchronous. Second, the orbit is circular. We discussed this as well, that the orbit is circular. Third, the orbit lies in the plane of the equator. This is correct. We discussed that it has a 0 degree inclination. That is what we mean by 0 degree inclination. So that's why this is also correct. Fourth is the orbit is at an altitude of 22,236 kilometers. Is this correct? No, absolutely not. How much is it? 35,786 kilometers. By this time, I have uttered this number so many times that you should, even in your dreams, you should remember that it is placed at 35,786 kilometers. So the fourth statement is wrong. And you have the fourth statement here, here, and here. So anyway, B, C, or D cannot be correct because of the fourth statement. So we anyway are left with only one statement, that is the first option, A. So why I said that this is an easy question? Because of statement number 4. Statement number 4 makes it very easy because you could use elimination to get to your correct answer here. Now there are other satellites. Now when it comes to the other satellites, we have the satellites which are meant for space science. For example, Astrosat, Mangalyaan, uh, the Gaganyaan mission, the Aditya L1 mission, the Chandrayaan missions. So all these missions are what? All these are missions which are meant for space science. So that's another category of our launchers. Similarly, we have experimental satellites. Now, what are experimental satellites? Experimental satellites, the name tells you, used for experiments. Wherever we are going to launch any satellite for conducting any experiment, whether it is a space science based experiment, whether it is a climate based experiment, a defense based experiment, so they will be called as experimental satellites. So that's why examples are INS 1A and 1B, where some of the critical components of upcoming missions were tested. Then there is a very, very important category of satellites which is called as small satellites. Now, what we mean by small satellites? Obviously, these are small satellites. When do we call something as a small satellite? When it is a satellite that weighs less than 500 kg. Any satellite with a weight of less than 500 kg will be called as a small satellite. So again, in this category also, there are different types of satellites. So we have something called as mini satellites. We have micro satellites. We have nano satellites. and we also have pico satellites. So there are all these different types of satellites. Mini satellites generally are the ones which are between 100 to 500 kg. Microsatellites usually 1 to 20 kg. Nanosatellites usually 1, sorry. Nanosatellites is correct, 1 to 20 kg. Microsatellites between 20 to 100 kg. And then lastly, we have picosatellites, which are less than 1 kg in mass. Less than 1 kg. So this is how we see that there are different categories of small satellites. Now, in this particular scenario, when we look at the small satellites, out of all these different categories of small satellites, the one that has become the most important satellite category is this, the category of nanosatellites. Today, what you'll find is that there are a lot of launches happening all across the world of nano satellites. Satellites that are just 1 kg in their mass, or 2 kg, 5 kg, 10 kg in their mass. These kind of satellites, they are being launched in very large numbers. So we have seen that there is a big market that has been created out of nano satellites. And these are not only government based launches, but many of these, or large, today you can say majority of these, are private launches, either being done by a private company, a private player, or maybe a company which needs a satellite. So that's why we have seen that there is a good growth that has happened in the market of nanosatellites. So that's why you can consider this as a question for your mains examination. Nanosatellite market growth. Look, this question, or this kind of a question, can be asked in various different ways. There can be multiple different ways in which UPSC can ask the same question. Answer, the points to that answer will more or less remain the same, with slight modification depending on how the question has been asked. Correct? Depending on how they have asked the question, you will change the way you are writing your answers, but largely the points will be very similar. What are these points? Just tell me some points. According to you, why do you think there is so much growth in this nano satellite market? What are the advantages of this nano satellite? You tell me points. If your points are correct, I'll keep writing. If you are missing some points, I'll write those points. But I want to start from you. Good. First point, many of you have written, it is cheaper or low cost. So yes, low cost. So this is very important point, correct point. Easier to launch. Yes, this is also correct. They are easier to launch compared to the bulkier satellites. Yes, they are lightweight, correct. What else? Recently, Kulasekrapatnam will discuss. Not today, perhaps tomorrow. We'll discuss about Kulasekrapatnam also. Fuel, very, very important point. Small in size, therefore contributes less to the space debris. Very good, very, very, very good point. So lesser space debris. Less space required for launching. It is a correct point, but not actually a relevant point in the growth of this market. So I'm skipping that point. Less e-waste. Yes, that's also correct. So less wastage. And not only e-waste, because there are metals also involved, there are plastics involved, there are glasses involved, there are a lot of semiconductors involved, so there are a lot of different parts. So it's not only about the e-waste, but rather the wastage in general. Private players, very very important. Helpful easily in private launches. Yes, less time consuming, very very important point again. Less time for construction. So that's why you can construct it faster and launch more. So this is a correct point, valid point. High accuracy is not really a point here, because for other satellites also precision is very high. There is one very important point that has been mentioned that hasn't been mentioned yet, I think. Ravi, you have mentioned this point, correct? Faris, you have mentioned this point, correct? Hmm. So one very very important point is the market growth or the employment opportunities that it presents. Employment opportunities, and from, if you look at from Indian perspective, this is something that also is very very crucial in revenue generation. It helps a lot when it comes to ISRO has been generating a lot of revenue, so it helps in revenue generation, it helps in employment opportunities, it creates a lot of services. For I think Ravi, you had mentioned about the downstream services. So that's why we see that there are a lot of opportunities and a lot of core sectors. There are a lot of core sectors that can grow along with. So that's why these are very very crucial in this context. And when you mention anything with regard to nanosatellite market growth, never forget to mention the role of NSIL or in space in India. I'm not discussing about this now or today, I'll discuss this tomorrow. So, the role of NSIL and in space, where we see that a lot of employment opportunities are coming up, it is overall looking towards a better growth of space sector. A lot of startups are coming up, a lot of startups are coming up, a lot of newer employment opportunities are generated, the companies are growing and becoming better, and we see that now a lot of private companies are also involved in the launches, correct? So there are all these things that are happening simultaneously. So that's why this becomes a very very crucial point, where we see that all these things are happening, and ISRO has been taking the help of a lot of private companies. So NSIL, in space, and also mentioning SSLV. All these things that we'll discuss a little later, not probably today, but tomorrow. So that's where there are all these points. Now, depending on what kind of question has been asked, in what context the question has been asked, you can pick and choose what point to use, what point not to choose, what should be used in that answer, what shouldn't be used in that answer, depends on what has been asked. And how much you will elaborate on this, how many stories you will write, also depends on the word limit. Whether it has been asked for a 150 words or 200 words or 250 words, depending on that, you can modify your answers. But these are some of the important points with regard to the growth of nanosatellite market. Now, lastly, we also have university or academic institute satellites. That these are the satellites which have been designed by some students along with maybe their faculty, and with the help of the university, they have also created these satellites, like Swayam Pratham. You have Kalam Sat, which has been in the news. So there are all these satellites. Now this also is very, very crucial, because this is how we see that how ISRO is trying to create some interest in the minds of the students, because all these launches are being done by ISRO, right? These launches are being done by ISRO, and for zero cost. The students don't have to pay, the colleges don't have to pay. All the launches are being done for free by ISRO. And why exactly are they doing that? Because they want to generate more interest in the minds of the students, that they should also believe that, okay, if I make a good satellite, a relevant satellite, ISRO is going to launch this satellite for me, which is very big. And this is something that can cater to this entire market growth. More students will come up, more students will join the industry. And even if they don't join ISRO, that's fine, but if they become a part of the Indian space market, that will be very, very useful in the growth of this entire sector. So that is precisely why we see that for the development of many of the nano or the pico satellites, we see that uh, we try to encourage the various universities and institutions to participate in this. Read this question. This was asked in your 2020 paper. Oh, sorry. There is, I forgot to change this. These two options are not correct. C is only 3 and D is 1, 2, and 3. I might have accidentally given you the answer. Please mark your answers. Hmm. 50% of you have marked D, which is the correct answer. 30% of you thought that because I'm making the change, so answer should be C. The correct answer actually is D. So the question says, for the measurement or estimation of which of the following are satellite images or remote sensing data used? The first statement is chlorophyll content in the vegetation of a specific location. Is this possible? Yes, it is possible. And how exactly can we measure the chlorophyll content? It's basically about the intensity or analysis of green color, right? So we try to understand how much green color has been used, right? How much of green color has been used, and that intensity of, I mean, how much green color can we observe from the satellite? So if the intensity of that green color is very high, that means that uh, photosynthesis is happening in a better way. So that's why intensity of green color is high. That means that this particular area is productive, it's more productive. So that's why these kind of images, they are very crucial in agricultural analysis. That if we find that the intensity of green color is not that good, it means that the productivity of that area is not that good, and we need to take certain measures so that we can improve the agriculture of that area. So that exactly is what can be done, and that's what one is correct. Second is greenhouse gas emissions from rice paddies of a specific location. What kind of greenhouse gas is emitted from rice paddies? Which is the greenhouse gas? Which greenhouse gas? Yes, methane. Correct. So it is basically, we are trying to identify methane emission, right? We are trying to measure methane emission. Can we do that? Yes, that's also possible with the analysis of the spectrometry analysis that we do of different gases. That can also help in understanding how much of greenhouse gases are being emitted, and various different gases can be measured with the help of satellites now. So we are actually doing that, so that's why this is also possible. Third one is land surface temperature of a specific location. Can we do this? Yes, we can. It basically is more about the infrared. We are measuring how much infrared radiations are being emitted from a particular location. So that analysis is also possible with the help of satellites. So that's why all these three are possible, and that's why this question was asked. Now, this question actually was also asked in the context of something called as HISIS satellite. This was launched by ISRO back in 2019. HISIS stands for Hyper Spectral Imaging Satellite. Hyperspectral imaging satellite. So that's why it is called as HISIS. And this hyperspectral imaging means that we are doing the imaging, or we are capturing the images from all the small parts of electromagnetic spectrum. That's why hyperspectral imaging, that every part of the spectrum is being used to take the images, whether it is the white light or infrared or microwaves or x-rays. All these kind of images can be taken with the help of the satellite, and that's why the name HISIS. Now this is something which is very crucial. That look, what happens is that when any satellite is launched, when HISIS satellite is being launched, the newspaper will tell you that it has agricultural applications, it has defense applications, and so on. The very first thing as an aspirant that you should do is first try to find the meaning of this term, hyperspectral imaging. Unfortunately, none of the newspapers were talking about this. This is what it means by the news analysis, that you go one step ahead and think of this, that if a hyperspectral imaging satellite is being launched, the very first thing that I should know as an aspirant is that what's the meaning of hyperspectral imaging. And if I know hyperspectral imaging, the meaning of it, all these three statements you will be able to mark without even knowing whether or not satellites are able to do this or not. So that's why these kind of understandings many a times they become very important. Now, coming to a very important discussion, Lagrange points. Now, Lagrange points, they become important because they have been in the news for various different reasons, and they have been in the news for at least last 3-4 years constantly. And that's why for the last 3-4 years constantly, I say this to every class, that this is a very important topic for this year's examination. So I'll say this again, that this is a very important topic for this year's examination, both for your prelims and mains examination. The question, although hasn't been asked in the last 3 years, I have been saying this, that this is an important topic. But let's hope that question comes this time and I'm proved to be correct, that this eventually is actually a correct answer, important topic for your paper. Why important? So recently we have launched this mission, the Aditya L1 mission, correct? So Aditya L1 mission goes to a Lagrange point called as L1, has been launched to this Lagrange point called as L1. Before this, the James Webb Space Telescope. This was also in the news, very prominently in the news. Where have we launched this? L2. Then, if you remember, when we were studying dark energy and dark matter, I discussed about one mission. Can you name that mission? Do you remember what I discussed? I named a mission which is supposed to study dark energy and dark matter. What is the name of that mission? Yes, Shimna, you've given the first correct answer. Pathan, correct. Yeah, correct. Prerna, correct. Why only four correct answers till now? You are not revising. The Euclid mission. So this Euclid mission, this also has been placed at L2. Then there have been a couple of Trojan asteroids in the news. There have been a couple of Trojan asteroids in the news. One is 2010 TK7 and the other one is 2020 XL5. And these two, they have been found at L4. These two have been found at L4. So that's why we see that constantly due to one reason or the other, they have been in the news. First, because of the discovery of 2020 XL5, it came in the news. Then James Webb Space Telescope was launched, came in the news. Then Euclid mission was launched, again came in the news. Now we named our mission Aditya L1 after this very point, that is Lagrange point, right? So now comes the question, what is a Lagrange point, right? Before that, Trojan asteroids. What do we mean by Trojan asteroids? So Trojan asteroids, these are asteroids which are not found in the asteroid belt. Correct? Most of the asteroids, we know that these asteroids are found in the asteroid belt, but these are asteroids which for some reason they are not in the asteroid belt, but they are traveling or they revolve around the sun along with the orbit of a certain planet. So they get stuck at a Lagrange point of any planet. Now we have discovered two Trojan asteroids which have been found at L4. Similarly, when you look at Jupiter, you'll find that Jupiter has a large number of these Trojan asteroids because simple reason, Jupiter is very near to the asteroid belt. That's why for the asteroids to get dislodged and get stuck at one of the Lagrange points of Jupiter is very easy. And for that also there is a mission, another mission that has been in the news, the Lucy mission. And this Lucy mission, this is a mission to study Trojan asteroids of Jupiter. To study Trojan asteroids of Jupiter. So this was also in the news a couple of years back. So that's why we see that there are all these things that in one way or the other are related to Lagrange points. So now coming to the question, what is a Lagrange point? Now, Lagrange points, these are very special points that are created because of gravity, gravity of a two body system. In this case, the two bodies are the sun and the earth. So the gravity of these two bodies, they create five special points. They create five special points which are called as Lagrange points. So as you can see, there is L1, L2, L3, L4 and L5. So all these points, these are basically, they are called as Lagrange points, and these are special points where we see that the gravity is balanced. The gravity is balanced, and that's why a particle, an object which is at one of these 5 points, they will remain around that point. They will remain at that particular point because the gravity is making that happen. Now, how are these hypothetical points? The answer is no. They are real points. These are real, rather than points, let's say regions, areas. These are areas where we find that there is a balance between the gravity of the earth and gravity of the sun. How are these points created? You can exactly mathematically calculate where exactly these points will be found between any two body system. Any two body system where one body is revolving around the other body, you will find these 5 points. So between the sun and the earth, between the sun and other planets, between the earth and the moon, between any two body system where one body is revolving around another body, these 5 points will be created. These five areas will be created, and where these areas are located, you can sorry, you can mathematically calculate that. How to calculate, way beyond the scope of our discussion, so no need to go there. Now in this particular scenario, what we see is that these points, for example L1, if you look at this point L1 is a point which is directly between the sun and the earth, right? Directly on the straight line that joins the sun and the earth, and it will always remain like this. As the earth revolves, L1 will also keep on revolving around with the earth like this. It will keep on revolving around along with the earth. So the relative positions will always remain fixed. So it's not that the earth goes here and L1 remains here. No, L1 will also go here. L2 will also go here. L4 will move here. L5 will move here. L3 will move here like this. So this entirely as a system would move. All right, this entirely as a system would move, and it's not that only the earth and the sun keeps on moving and all the other points they remain stationary. No, they all will keep on moving. So that's why remember this, that all these are special points and they will move along with the earth, and not only the earth, with for any two body system where one is revolving around the other. So that's why this is something that will happen, that let's say we have the earth which moves here. All right, suppose that the earth has moved to this point. So what then happens is that this is the straight line joining the sun and the earth. So now L1 moves here. L1 now will be found here. L2 moves here. So now L2 will be found here. Similarly, by the same angle, L4 will also would have moved. So now L4 would have moved here. Similarly, L5 would have moved here. And on the other side, L3 would have moved here like this. So as this moves, every other point would also relatively move. All right. So just remember that these are points which always remain fixed, relatively fixed with regard to one another. Now, also understand the importance of these points. That why are we launching Aditya L1 to L1? Why are we launching James Webb and the Euclid to L2? Why? Look at L1. L1 is directly in line with the sun, correct? And it always will keep facing the sun. If it was a normal orbit, what would have happened? That it would be moving around the earth. So sometimes it will be facing the sun, sometimes it will come back. So then it will not have the access to the sun. But when you are at L1, from L1, it has 24-hour access to the sun. So what better way to observe the sun? Aditya L1 is supposed to observe the sun. So, what better place to be at if you want to observe the sun? And that's the reason why we wanted to place Aditya L1 to L1. Because we knew that this is the place where it could make the best observations and it can remain there for a long time without any problem. Then, why to choose James Webb, or for Euclid or the James Webb mission? Why did we choose L2? The reason is just the opposite of what we discussed for Aditya L1. Because once you are at L2, you are completely shielded from the sun. Correct? This is a point, as you can see, that this is a point which is located behind the earth. So the rays of the sun, they don't reach L2. Right? The radiations from the sun, the heat from the sun doesn't reach L2. And because they don't reach L2, it's safer to keep these instruments there. At the same time, these are telescopes. They have to take observations. And if they have to make observations of the night sky, of the space, they should be devoid of any external light. And that is what happens here. Because otherwise, if they were facing the sun, we would need a lot of shields, first of all, so that we can shield them from the harmful radiations of the sun. And secondly, due to the strong presence of sunlight, it would become extremely difficult for them to take any observation. So that is the reason why L2 has been chosen, because it lies in the shadow of the earth. So that's where we see that there is an importance of L1 and L2. Even for L4 and L5, these are very stable points. The reason why majority of the Trojan asteroids, wherever they are found, you will find that they are either found at L4 or they are found at L5. For this very reason, because compared to L1, L2, and L3, L4 and L5 are very stable points. They are very stable points as compared to L1, L2, or L3. That is the reason why we have discovered so many asteroids at either L4 or L5. Now, is there a use for L3? Sitting on the earth, I would say no. Because first, just imagine that there is this big giant ball of gases, that is the sun, that lies between us and L3. So, communicating with L3 is a big challenge. So, that's why we don't find real applications for L3. Only if you are an alien, then L3 is probably the best point for you to keep your spaceship. Nobody from the earth will know that you are at L3. Then you can launch your attack on the earth from L3 very easy. So if that was the case, and I'm sure and I hope that none of you are an alien and you are not planning to attack on the earth. So Lagrange points. So positions in space where gravitational forces of two body system like the sun and the earth produce enhanced regions of attraction and repulsion. And these are five special points. There are three stable points labeled as L4 and L5, and there are three unstable points which are labeled as L1, L2, and L3. So that's why we see that these points they become important. So what exactly is this point doing? It is a balance, right? Balance of the gravitational force, correct? Is a balance of the gravitational force which is creating these five special points. So that's why also remember the importance of L1 and L2. That why exactly are we launching Aditya L1 to L1? Because L1 directly in line with the sun. So an important point to observe the sun, right? That's why an important point to observe the sun. And with L2, this lies behind the earth. So shielded from the harsh light and radiations of the sun, harsh light and radiations of the sun, thus a great point to keep telescopes. So that is why L1 and L2 they especially are very crucial. And when it comes to L4 and L5, very stable compared to other points, compared to other Lagrange points. Hence, most of the asteroids are found here. All right. So that is why these points are important. So now, with regard to this, what we see is that Aditya L1 especially has been in the news, right? So, for example, we see that there are now also understand, and probably I'll discuss this with you very soon, uh, because I'll take some current affairs sessions separately also for prelims 2024. But with Aditya L1, any news that you come across, just also understand how to read that news. Many times one small news here and there about Aditya L1 will keep coming. So just understand how to see that news. So for example, if you look at this news, December 2023, Aditya L1 unveils full disk images of sun. Telescope aboard uses 11 filters to show new details. Now here we are talking about a specific instrument that we have on Aditya L1, that is SOOT. And it is basically designed to observe the sun in near ultraviolet wavelength range, and that's why it is called as SOOT, because it is sun ultraviolet imaging telescope, something like this. So its primary goal is to understand the processes occurring in the solar photosphere and chromosphere, which are the outermost layers of the sun. So we know that you have photosphere, then you have chromosphere, then you have corona. So basically this is where we are making the use. And what exactly is it doing? It's taking ultraviolet images or near ultraviolet images using certain filters like this. So these images were actually published by SOOT. So just like how we use filters on our Instagram accounts, similarly they have used filters to come out with all these images. So that's basically what we see with SOOT. So these kind of uh, news will be there. So just when this news comes, just understand what exactly does SOOT do. What is its role? In one line, two lines maximum. Don't go into the technical details of the same. Just know this much enough. Similarly, this was also in the news. Aditya L1's PAPA, or Plasma Analyzer Package for Aditya, detects impact of coronal mass ejections on solar wind. So here, what exactly? Again, a very peculiar name, Papa. It has been designed for what? Designed for in situ measurements of solar wind electrons and ions. And there are two sensors that you have on board. One is sweep and one is swikar. So these are the two which have, and they are capable of measuring the electrons and ions over specific energy and mass ranges, as well as the direction of arrival of solar wind particles. So that's why the electrons that are being emitted out of the corona, or the ions that are being emitted, they can capture that, they can study them, and they can understand the specific mass and the energy ranges of all these particles. So that's why they give us a better analysis of the coronal mass ejection. So that's why we see that there are all these kind of news, and this was in the news in February 2024. So that's why whenever these kind of news come, another one, if you see January 2024, ISRO successfully deploys magnetometer boom on Aditya L1 in halo orbit. So again, when it comes, so there is this term that they have used, magnetometer boom. So what is it? It is basically structural component on a spacecraft, which is basically designed to extend the magnetometer away from the main body of the spacecraft. So basically, this is what will open up the magnetometer so that it can take the required observations. So that is exactly what it is with regard to this. And it also will try to ensure that it minimizes the interference of from the same spacecraft's own magnetic field as well, ensuring more accurate measurements of the surrounding space magnetic environment. So if you look at Aditya L1, you'll see that there are all these different uh, payloads that we have on board. So magnetometer, Papa, Helios, and Suit, they already have been in the news. So that's why just remember these things in just one or two lines. Because if at all they have to ask a question in your prelims examination, they won't go beyond this. All right, they won't go beyond this. They'll ask this much and not beyond this. Now coming to a very small topic, and this is the last kind of orbit, and this is GTO, or geosynchronous transfer orbit. Geosynchronous transfer orbit. Now understand, what is this orbit? What exactly is this orbit? So if you look at this figure, what you see is that this is a orbit that will be used to place a satellite in the high earth orbit. Now why exactly do we need this? Understand this. Any launcher that we are using, any launcher, a PSLV, a GSLV, an SSLV, or any of the other launchers that NASA has or European Space Agency has, whatever, none of the launchers, none of the launchers, they are not capable of going beyond a certain point, beyond like 2000 kilometers. That's it. So a launcher is not able to go up to 35,786 kilometers. It goes only up to 2000, 3000 kilometers. Beyond that, the mechanism of geosynchronous transfer orbit will take it to the required orbit. That is where we need this orbit. So understand the requirement. No launcher is capable of carrying a satellite beyond approximately 2000 kilometers. This is where the mechanism of geosynchronous transfer orbit carries the satellite to the geosynchronous or geostationary orbit. So that is basically what happens. That for the first 2000 kilometers, it is the launch vehicle that will carry the satellite, and beyond that, it is physics that will carry the satellite. So if you have seen, for example, so this is something that will happen. That from here on, another thrust will be provided, more thrust will be provided, but basically we are exerting more force on the satellite, and then the satellite will go to the required orbit and start orbiting from that orbit. So this is what happens in a transfer orbit. Even for the Chandrayaan mission, you might have seen these kind of images where it shows that how from the earth to the moon, how we are carrying the satellite. Like this, you might have seen that, like this, it keeps on increasing in its orbit, and then after that it goes like this on the moon. Correct? So something like this. So this is another example of a transfer orbit. So there are various ways in which transfer orbits can work. So largely they would carry the satellite from the low earth orbit to the high earth orbit, or to the required orbit. Right. So this is it about this section. We'll start with the next section in tomorrow's class. We'll discuss about the launchers. We'll discuss about ISRO. We'll discuss about a couple of miscellaneous topics. And then in the second half of tomorrow's lecture, we'll start with our new chapter, that is biotechnology. So we'll start with biotechnology in tomorrow's class. So if you have any questions, please ask your questions now. Meanwhile, I'll also post the leaderboard for today. So this is the leaderboard. So three of you have all correct, and congratulations to you, Vishant, Shahid, and Faris, sorry. And then a lot of you also have gotten just one wrong. That's okay. I hope you understand what went wrong for you. What is exactly meant by stable and unstable points? Okay, so what we mean by stable and unstable is that the forces that are acting on L1, L2, and L3, they make that point itself very unstable, and it is not easy to keep something at L1, L2, and L3. Compared to that, at L4 and L5, we get bigger areas, easier areas to keep it. You can just imagine, you can just think of L1, L2, and L3 like mountain tops, and think of L4 and L5 like plateaus. That it's easier to keep something on a plateau as compared to keeping something on a hilltop or a mountain top. So that is the basic difference there, and that's why we say that L4 and L5 are more stable. If the mobile companies all use IRNSs in India, then if we go to other countries, does it become a problem to navigate there? No, it doesn't become a problem, because they would have that option that the chip can change and they can actually start using the navigation systems locally there. HISIS meaning, as I told you, hyperspectral imaging satellite, meaning that we are doing hyperspectral imaging, meaning that each and every part of the electromagnetic spectrum, whether it is a wavelength of radio waves, whether it is a wavelength of microwaves, whether it is a wavelength of infrared, so all these things, all these different electromagnetic spectrum, they can take the images. Last point of GU and GSO, I could not understand. So last point basically was that what I told you is that in case of geostationary Earth orbit, all the three parameters, height, shape, and inclination, they are all fixed. So because all these things are fixed, there is only one such orbit possible. There could have been another orbit possible only if there could have been a variation in these different parameters. Correct? Because height is fixed, meaning that the radius is fixed. Shape is fixed because it is circular. There is no variation in circular. There are variations in elliptical shape, but no variations in circle. And even the angle is fixed. They cannot be inclined. So that's why they are a unique orbit. That is what we meant. What about other small satellites? Because nanosatellites is given the priority. See, nanosatellites have been given the priority because they have been found to be the most useful. Because they are the most useful, that's why they have been given the priority. But yes, we do launch a lot of microsatellites also. We do launch a lot of picosatellites also. So it's not that they are not being launched, but we see that nanosatellites for us are the sweet spot. And that's why the launches are higher in number. So please show Papa slide. The Papa slide. Yeah, this is the one. Synchronous means that it has been synced. All right, we have synced it to something. So when we say geosynchronous, why geosynchronous? Because it has been synced with the rotation of the earth. 24 hours, what is the value of what is the significance of 24 hours? That the earth rotates in 24 hours. So if a satellite is taking 24 hours to revolve, it means that it is fixed with regards to a point on the earth, and that is why it is being called as geostationary, because a satellite which is at geostationary orbit will look to be stationary with regard to what we see, and that's why geostationary or geosynchronous, because synced with, it has been synchronized with the rotation of the earth. Similarly, sun synchronous, because it has been synchronized with the local solar time of a place or the movement of the sun over that place. So that is what we mean by synchronous. Lagrange point is, yeah, this is the Lagrange point slide. What is Papa? Basically, it is nothing but something that can study the emission of electrons. The electrons and the other charged particles, they can be detected with the help of it. So can we go? Yeah, I mean, if you don't have any questions, if it's all clear for you, you can absolutely leave. Hmm. So I think I've answered most of the questions that I had here. So if you have further questions, you can again bring the questions back tomorrow. Please go back and revise everything that we discussed today. Tomorrow we shall end this chapter and we'll move on to our next chapter, that is biotechnology. Thank you very much. Until then, good night.